Okay, here we go. Sorry about the delay. All set up here. Okay, here we go. I want you to take a look at something, please. This is the topic du jour. Okay, so implicit differentiation. What in the world is that? Well, in order to know what that is, I want you to know that what you've been doing is called explicit differentiation. Explicit differentiation means when you're differentiating for a variable that is isolated. Okay. Explicit differentiation means so explicit differentiation would be something, all the stuff you've done where y equals some explicit function of x, where the y's and the x's are separated by the equal sign. Okay. Implicit differentiation is going to be a little bit different. It's very convenient. In some cases it's convenient, in some cases it's absolutely necessary. Now, to get I think a good way to introduce this is to look at a relatively simple function, and let's talk about how we would differentiate this. So, and when I say differentiate, I guess I should be more specific. I want you to find dy dx. Okay. So, suggestions. First of all, what does that look like? If I were to graph x equals y squared, what's that look like? You know? What do you have there? Okay, yeah. So a sideways parabola. Good. Yeah. Okay. And we could convince ourselves of that pretty easily because we know that if I were to take a different function, if I were to take instead the function, say, y equals x squared, I know what that looks like, right? That's just a normal parabola. And if I graph these two things, it'll remind you about an interesting relationship here. If I take the blue function and I graph that, there it is. Y equals x squared. Now, how are these two relations related? X equals y squared and y equals x squared. They have a specific relationship. And all I've done is I've just interchanged the x's and the y's. Right? Does that sound familiar? Very good. Okay, it's reflected over the line y equals x. What do I call this relationship when I interchange the x's and the y's, when I trade the x's and the y's? You got the hard part. You know what the relationship is, what the graphs of the two, how they're related. These are just called inverses, right? When we interchange the x's and the y's, those are inverse relations. Okay, so if this is the blue one, and here's the line y equals x, here's the line y equals x, then all I've got to do is just reflect that over the line y equals x. Now I'm going to give you a little easier way to think about that. It's kind of tough. We're much better at reflecting things over vertical and horizontal lines than diagonal lines. It's kind of hard to think about how to do that. What you can always do instead, if you want to go from a function to its inverse, or vice versa, doesn't matter. All you have to do is two steps. You're going to rotate everything about the origin 90 degrees counterclockwise, which is pretty easy to visualize. right? So the horseshoe ends up being sideways, opening up to the left, right? And then you reflect it over the y-axis. Those two things magically will always create the graph of an inverse. Okay? So you can kind of see what that's going to do then. If I rotate it this way and then reflect the whole thing over the y-axis, don't I get something like this? Right? And so there's my graph. Now, is that a function? The blue one is, but the black one's not, right? How come? Vertical line test. Okay, good. So we're dealing with a non-function here. And we'll come back to this graph, but we don't even need that necessarily at the moment. If I want to find dy dx, does anybody have any ideas how I might approach that? And the only game you guys know right now is explicit differentiation, where if I'm trying to find dy dx, every time you've done that, you've had y as some y equals some function of x. So make it like that. Okay, so how can I do that? How solve for y is, I guess, what you're saying, right? Algebraically, I would square root both sides. And what do I have to do if I square root both sides? What do I have to include? Plus or minus. Good. So if I do that, then I'm going to get, I'll go to the next page for a second here. I'm going to get something like this. I'm going to break this into two parts. We started off with x squared equals, no, x equals y squared. Whoops. And we're going to split this thing up. We're going to get either y equals the square root of x, or y equals negative the square root of x, right? You told me plus or minus the square root of x, right? And both of those are derivatives that I can do. Let's focus on the blue one first. If I want to differentiate that, what do I have to do first? Okay, write the radical as a fractional exponent. So I could write that as y equals x to the 1/2. So now if I take a derivative, I get 1/2 x to the, which finally I could write as 1/2, whoops, about 1/2 times the square root of x. Okay, look good? Okay, other side, very similar. Right, only difference being I've got that minus sign there, but otherwise it looks the same, doesn't it? So, y equals negative x to the 1/2. If I differentiate, when all the dust settles, aren't I just going to get y equals negative 1/2 times the square root of x? Get that minus sign out front. Okay, now here's my challenge, and you might wonder why would we do this. Can you write these answers in terms of the original functions? So this is kind of what we call in math a recursive process in a way here, right? We're going to write y prime in terms of y. Pretty easy over here, isn't it? What did we start off with y being in the blue side of the board? Square root of x. And so there's a y right there, isn't it? Right? Okay, so this just becomes a y, and I end up with y dx equals 1/2 y, right? Now what about on the other side? What's my y on this side? Okay, it's a negative square root of x. But I can group these factors any way I want to. It's, of course, more convenient to put that negative sign on the top, but I don't have to necessarily, right? I could group that negative sign with any of my three factors, and I'm going to get the same result, right? So let's just mix and match just for a second here. Let's do this. Let's say y equals 1/2 times negative the square root of x. And now, what do you notice? If I plug in for y, the original y, it looks the same, doesn't it? How about that? Now there's a potential advantage, right? So we get the same looking derivative. That's supposed to be dy prime. dy dx equals 1 over 2. Oops. Right? Okay. And usually that's not something we'd want to do, but maybe we notice, we notice from that, well, it becomes clearer how we might have an alternate way of doing this derivative without having to split it into two explicit functions. Okay, maybe we could try something a little different. Let's start with, just like we did before, let's start with x equals y squared, and let's just differentiate with respect to x implicitly. We're not going to worry about solving for y. We're just going to use the chain rule and differentiate both sides with respect to x. Okay, so what happens if we do that? So if I differentiate both sides with respect to x, I'm going to get the derivative with respect to x of x on the left equals the derivative with respect to x of y squared on the right. Well, what's the derivative of x with respect to x? 1, right? And I know that because that's one of my standard forms, but I could even see it algebraically. I would just end up with dx over dx, and algebraically those just cancel to 1, right? Either way you want to look at it, they're both equally good. I just get 1 on the left side. Now, what about the right side? If you look careful with this, if I'm going to differentiate y squared with respect to x, there are 2 layers there, aren't there? Right? I've got the derivative of something squared. Well, what's the derivative of something? Something squared, sorry. 2 something to the 1, right? So I end up with 2 times my something, which is a y. And then if I peel that away and look inside, what's the derivative of y with respect to x? dy dx, right? So there's my dy dx. Okay. Now, if I algebraically solve for dy dx, what am I going to get? Well, you know, 1 over 2y. How about that? Good trick, right? I solve for this in terms of my original function. Yes, ma'am? Oh, okay, right, okay. So if we want to algebraically, if I just want to isolate this, right, I've got to divide both sides through. Divide both sides by 2y. Right, that's all I'm doing is now I'm just algebraically getting that derivative by itself. And I end up with that. Right? Okay? So you see how that might be useful. And then if I wanted to split that up into separate functions, I know that my derivative is 1 over 2y. Well then, if I choose to, I could go back and algebraically solve for y in terms of the 2 functions that build it. Yes, Alicia? How did I get the dy down here, you mean? Because of the chain rule. Okay, because of the chain rule. Now, you know how to do, what if I did, let's do another quick example. Okay, what if I did this? What if I had the derivative with respect to x of, let's say, x plus 1 squared. Going back to stuff we've already done. That's a chain rule problem, isn't it? I've got 2 layers. I've got the derivative of tan squared. So that's going to equal 2 times tan times the derivative of tan, which is in this case just going to be a 2, right? But it's really a 2 dx dx, isn't it? Right? If I take the derivative with respect to x of 2x plus 1, I'm going to get 2 times dx dx, which we never write because it's just 1. Everybody see that? Right? That's really all I'm doing, but the dx dx part just goes away. Now, if the variables were different, though, it wouldn't go away. If that had been like a 2y plus 1 in there, then I would have had 2 times, in this case it's 2x plus 1, but it could have been 2y plus 1. But when I took the derivative of the inside, instead of just being 2, I'm going to get 2 dy dx because the variables don't match up, right? Okay. This is true. If I say the derivative with respect to x of x, I just get 1. If I say the derivative with respect to x of y, I get dy dx or y prime. But if I said the derivative of y, whoops, if I said the derivative of y with respect to y, what would I get for an answer? 1, yeah, because the variables match. When they don't match, though, I get an actual derivative that doesn't go to 1. Okay. Now, you might have noticed, I gave you guys a sheet of derivatives, right, a while back, and they might have looked a little bit funny. They were written in terms of u's, typically, and this is not a big deal. Let me just draw this to your attention. This is something that'll be really easy. If you haven't already pieced this together, it'll just take a second. What we're able to do with the chain rule is we can extend all our original. We started off with some really simple forms of derivatives. For example, we said something like this. We said that the derivative with respect to x of sine x equals cosine x. Okay, but we can do better than that. Instead of just limiting ourselves to the derivative with respect to x of sine of x, we could have sine of anything, really. It could be sine of any function of x. It could be sine of x squared, or sine of tangent of x, or whatever you want it to be. I could instead rewrite that as the derivative with respect to x of sine u, where u is understood to be just some random function of x. And then what was our answer to that? Cosine u times du dx, right? Cosine u times u prime. That's sort of our chain rule strengthened version of our standard form. Now, it doesn't have to be a u. It could be a y, right? U is just, it could be anything, it could be any function of x, or it could be any other variable for that matter. We're just giving ourselves the opportunity to differentiate with respect to x signs of something else, some other variable. Okay? So that's all we've done here. If we go back to this implicit differentiation problem, is we have just allowed ourselves to differentiate straight through and get answers in terms of the original variable. But we didn't have to go through the task of solving for y in terms of x. Right? Now we could have. If we go back to our picture, look what we were able to do with this. We were able to take this x equals y squared and we can split it up. It's a non-function, right? Because it violates the vertical line test. But if we break it apart, we can break it apart into two separate individual functions. On the top, I've got y equals positive the square root of x. On the bottom, I've got y equals negative the square root of x. And by the way, this is, you're going to start to appreciate here more and more. When you solve explicitly for y in terms of x in any kind of a relation, that's all you're doing, by the way, is you're splitting it up into separate functions, cutting it into pieces, each of which independently is a function, right? Taken together, it was a relation that was not a function, but separately they're functions, and then all I did was just treat them one at a time, right? But the beauty of what we did was we didn't have to do that. We got an answer in terms of y, and if we want to go back after the fact and solve for y in terms of x, great, we can do that. I could say that y equals plus or minus the square root of x, and so I'd get two answers, 1 over 2 times the square root of x and 1 over 2 times negative the square root of x, right? Handy. Sometimes not just handy, sometimes absolutely essential. Give you an example. This was convenient. I'll give you an example where it's more than just convenient. Say we start off with something really ugly like this. Okay, say I want you to find y prime, which is just dy dx. Can you solve for y in terms of x that time? I don't think so. That's going to be pretty hard to do. Right? That's going to get seriously complicated if it's even a tractable problem. It's going to be really, really complicated. But we could make this a very simple derivative by just differentiating implicitly. Just use the chain rule and differentiate both sides with respect to x. And it's no big deal. What happens on the left side if I differentiate both sides with respect to x? What does the chain rule give me from that first term? You get two layers, don't I? Derivative of something squared is just 2 something to the 1, and then the derivative of y with respect to x is? Yeah, I'll just write it as y prime. How about that? And that's a good idea, by the way. Otherwise, it gets really visually confusing. So we'll write it as y prime. Next term. Right, and I could even, if I want to, just maybe pull that 3 out. Okay, and then I've got a product rule, don't I? Right, so what's that going to give me then? If I do first times derivative of the second, I'm going to get x squared, and then the derivative of y squared. We just did that, right? Wasn't that just times 2y prime? Okay, plus the second times the derivative of the first. And what's the derivative of x squared with respect to x? Just 2x, right? The dx we wouldn't even bother writing. Just 2x. Okay. And then finally, minus, what's the derivative of x to the fourth with respect to x? 4x cubed. And then on the other side, the derivative of 9, 0. Okay, now all I've got to do, I got to distribute the 3, sure. But then notice that all the y primes are going to always be linear, aren't they? Because they're just tacked on to the end. They're just going to be one link in the derivative chain, right? And so you're never going to get something like a y prime squared. It can't happen because it's just you're always going to get that single y prime because you're differentiating the variable y with respect to x. At some point in that chain rule process, if there's a y mixed into the derivative, you're going to differentiate that layer where you're simply just differentiating, one layer of the onion, which is a y with respect to x. So it's not an accident that these all worked out so nice. This can be really easy algebra, though, isn't it? All we got to do to isolate y prime is just push all the y prime terms to one side, all the other junk to the other side, factor out a y prime, and divide the rest away. You see that? Let's watch it happen. But that's always the way it's going to work. So let's do a couple things at once here. How about if we distribute the 3 and we'll collect all the y prime terms on the left, all the terms of the red part, or the red factor. So we've got a 2y prime plus, 6x squared y prime? Everybody see that if I distribute the 3? 6x squared y prime. And everything else, all the other terms don't have y primes in them, so let's stick them on the other side. So we're going to get a minus 6, whoops, not 6, not 2, 6, minus 6x y squared plus 4x cubed. Everybody agree? Okay. And then I could factor out a y prime on this side. Wouldn't I just be left with 2y plus 6x squared y? I'll put the positive term first, how about? And then all I have to do is divide both sides through by that factor, by the leftover after my factoring process. And I get y prime equals 4x cubed minus 6x y squared all over 2y plus 6 x squared y. It's a mess, but who cares? We don't care, because remember what the derivative is for. It is for calculating slopes, right? Slopes of the curve, or tangents of the curve, however you want to think of it. And in order to do that, I've got to be able to plug in values of x, and in this case, y also. Okay, so I'm just going to plug numbers in for x and y, and then even though this looks ugly, it's going to be simple then. It's going to be a bunch of numbers that I gather into a fraction, right? Okay, so that's what it's about. Now, is it strange that we get y's in our answer here? Yeah, compared to stuff we've been doing, it's a little bit weird. But remember that what we're dealing with here is not necessarily a function. It's some weird looking relation that probably is not a function. It violates the vertical line test. And so if I look at a graph of something like that, it makes sense that I would have y's in my answer, because let's just say this is arbitrarily, let's say this is what my function looks like. I mean, it could be real bizarre, right? If I take this point, like for example, at x equals negative 5, for example. Well, look, there's multiple places where x could equal negative 5. So if I want to know the slope of this relation, I have to specify not only x equals negative 5, but maybe also y equals 4, right? So I have to pin this down horizontally and vertically. And so it's not a mistake. It's not weird that I have y's in my answer. Okay? Let's try, how about, they're just talking about that. Let's do one like that. Find line tangent to the relation x squared plus y squared equals 4 when x equals square root of 2. Now, what is that relation? Can anybody recognize that? X squared plus y squared equals 4. Recognize that? Well, it is. It is, in fact. That's part of it. This is a circle centered on the origin with radius 2. Okay. What that is. So if I ask for the line tangent to this thing when x equals the square root of 2, in your mind you might be thinking, well, if it's a circle, it might be 2 of them, right? Think about that, because on a circle, all but the very edges, there are going to be 2 points that line up vertically on a circle if I cut through it vertically, right? And we'll look at that in a second. But let's just do the math. Let's not worry about, I mean, it's nice to kind of use a little foresight here and think ahead, but let's just do the math. If I want to find the tangent line, I need a point and a slope, right? Okay, well, to get a slope, I need a derivative. So let's differentiate. And rather than trying to solve for y in terms of x, that's a lot of work. Let's not. Let's just use our new trick, implicit differentiation. So what do I get if I implicitly differentiate this? On the left, derivative of the first term is? Second term? Good, 2y, and then I've got the derivative of y is a y prime. Equals 0. Good. Okay, so to solve for y prime, I can subtract 2x, divide by 2y, right? And what am I going to get if I do that? Y prime equals negative x over y, negative 2x over 2y, and the 2's cancel, right? Okay. So I get x's and y's in my answer. So I get two answers, right? I'm going to get two answers here. When x equals the square root of 2, there are multiple possibilities for y, and I can see that by plugging this value into my original function. That's kind of a slick little trick, right? If I want to know what's the value of y for a given value of x, just like before, I substitute. But look what happens. If I substitute the square root of 2 in there, I'm going to get, what, 2 plus y squared equals 4. Y squared equals 2. So what does y equal? Plus or minus the square root of 2. So I get two answers, right? I'm going to get two different answers for this. I'm going to get one answer when y equals the square root of 2. And let's just try that one. So when y equals the square root of 2, y prime is going to equal what? And we already know we're evaluating this. I should have both parts there. Where y equals the square root of 2 and x equals the square root of 2. What am I going to get for y prime? Negative 1, aren't I? Right? Good. Negative square root of 2 over square root of 2. So m equals negative 1, and I've got the point, square root of 2, square root of 2, right? So I can build a line from that stuff. Now when x equals the square root of 2 and y equals minus the square root of 2, what's my slope? 1. Yeah. M equals 1, and I've got the point square root of 2 minus square root of 2. And I can build those lines pretty easily. Let's go ahead and do that. So I'm going to get what? Y equals negative, mx plus b. So negative x plus b. Let's solve for b by plugging in these points. Square root of 2 equals negative square root of 2 plus b. So b is 2 times the square root of 2. Okay. Okay. So that gives us the line y equals negative x plus 2 root 2. What about over here? Y equals 1x plus b. So I get negative square root of 2 equals square root of 2 plus b. So what's b? Negative 2 square root of 2. Good. And so I get the answer y equals x minus 2 root 2. Okay, let's just look at those on a graph. I got this new fancy piece of software, and I'm not very good at using it, but I'm going to try it. Is that it? I think that's it. Well, I'm going to run out of time anyway, aren't I? Well, that's not what I want. Seating chart maker. No, that wasn't it. The calculus of a seating chart. There's a lot of math involved.